You say hi already?
Just that again.
You say hi again.
I'm Cameron.
I'm Jack. I'm Callum.
I'm Louis. This is our vertical wind turbine project. Wait, Jack, are you still?
Started the project, we brainstormed some ideas such as the trailer windmill, a go-kart, the automated well and the scale electric car. Once we'd came up with some ideas, we put them into a decision matrix where we established that the best one for the project would be the windmill because it just came out with the highest score. Some of the reasons the other ones didn't fit the brief that well were because of the cost or we didn't have the skills to make them.
The idea was to attach the turbine on the back of a trailer which would go onto a bike. This would create air resistance for the turbine to spin whilst it was moving on the back of the bike. This was impractical, there was no space for the battery or anything to make the actual energy from. So we made a car roof rack to go onto the turbine would attach to it with a hinge which would make it go from horizontal to vertical to allow it to get its air resistance. But again, this was impractical. So then we decided to make a standalone turbine, which would stand on a pole. This was more practical for us as we could make it in the workshop. These are the sketches that we made. As you can see, like just little designs of the turbine and that.
The idea and preliminary research. We all did individual research and then we did group research. So we brought the individual research over towards the group because obviously 6 heads is better than one. So we decided to go for a vertical wind turbine, like that one, over a horizontal wind turbine because of multiple reasons. Some being that the wind turbine, with it being vertical, it would be easier to make, so you wouldn't have to worry about balancing because there was a lot of advanced maths worrying in the maths about it, and it's not worth the time, it's not really efficient. It takes up a lot less space, so if you think about a big, massive horizontal wind turbine and a small little vertical one that we've got, it's a lot more compact so it can go into smaller spaces. It's a lot cheaper to produce because you can make them out of small, like cheaper materials, you can make smaller versions of it and it'll still work just as effectively. And it requires less wind because of the angle of the blades and how there's more of them than on a horizontal wind turbine. It requires less wind to get going. And with the vertical wind turbine, it can be made a lot cheaper than a horizontal one. So, for example, ours was made from readily available materials like a bicycle wheel, which we picked up from a scrapyard, from PVC guttering pipes, which again we can get really cheap second hand, or we could get from a scrapyard, junkyard, whatever, and just basic bits of steel which we could have made, crafted, found, whatever. When it comes to generating electricity, we needed to really think about how we were going to get it going. So we decided to use 2 permanent magnet motors, as these would be the most efficient and easiest to make, or not make, but easiest to make electricity. To figure out which ones we had to use, we had to figure out the voltage to RPM ratio, and then once we figured that out, we needed to then think about what motors we needed to get, which would be ideal for the wind turbine. And we also needed to make sure they produced enough voltage to get over the potential difference from the battery. You know, have to go through the charge controller, charge the battery, and also operate a load, which in our case would be a phone charging on a standard 5 volt. So yeah.
The downpipe structure was 2.5 metre PVC pipes, which we got from the plumbing department, joined in the middle with a PVC joining piece. This was a weakness. We later adapted it using kind of a dowel, which is a wooden joint through the middle to try and strengthen it. We also used 2 bongs, which are bits of wood in either end, to stop the brackets from crushing the PVC pipe. Nylon guide ropes, and chocks were used to kind of hold the pipes upright and structure straight. It was up, and the chocks were so that you could tighten the guide ropes or loosen them to how tight or loose they needed to be. Pegs we used to peg out the guide ropes. We made these from mild steel, which was bent to kind of make it strong and hold the guide ropes underneath. The spike bracket for the bottom bolted onto the PVC pipes, and it was made from kind of scrap bits of mild steel to make a point, and the tapped holes for the bolts to kind of secure it to the pipe. The upper turbine bracket was similar, using bolts to kind of fasten onto the pipe, and it's what, as you can see here, everything's mounted on and the turbine sits on top of. This was done by cutting a section of mild steel pipe, threading holes and welding a plate on top of it. We used kind of hand adjustable bolts, which were normal bolts with kind of bits of metal welded on top so that you can tighten or loosen them by hand. Turbine wheel, bush and quick release was kind of mostly a wheel that we fastened to the bracket so that the quick release could easily take on or off. The wheel, bush and quick release was all made from a mountain bike wheel. We used a quick release assembly to attach the axle into our bracket, which meant that kind of we had an upright axle that we could fasten the wheel on top of. The quick release bit meant that we could take the wheel on and off to make it transportable. To make sure that the wheel sat right and secure, we used a bush, like a little grass bush, and some washers to hold it on. As you can see here, the kind of axle sits through the wheel and is fastened to the bracket. The blades were just cut from guttering. I think they're 1 metre in length each. We found that on the first testing they kind of wobbled a bit, so we added these support brackets, but we probably can stop using them in future to make it easier to take apart and assemble and make it easier to transport. The motor brackets was this kind of long piece of mild steel. It's got a hole to sit on the axle and it's welded on top of the bracket. It's got holes here for the motors to sit through and they're fastened through with screws. The pulley wheels and belts are made from nylon. It's made from a nylon bar shaped on the lathe. Here there's bolts that kind of fasten to the flat edge of the motor axle so that they don't spin free from the motors, and they've got grooves kind of to house the belts so that it can spin. Underneath the one that's attached to the actual wheel, there's a kind of big space so that there's room for it to spin free from the bush, and it's just kind of bolted straight onto, screwed straight onto that wheel.
First test that we did, and as you can see there's a lot of buildings around and there wasn't much wind on this day, but we're still getting quite a bit of movement. So in an open field you can imagine we get quite a lot of energy being produced from that. After this though, we did try and we added some brackets to strengthen the blades to stop the flex because they were bending quite a bit. We also, this is at half height, we did try it at full height but it wasn't very stable. The centre was bending quite a bit. So we had a dowel to fix that problem. They're testing. We're testing the guide rail blend just to see how stable it is with them up. When you hold them out. There's a lot of buildings around as well, so the wind flow wasn't great on this day. So in an open field again, it would probably be a lot better.
So on this slide, we talked about problem solving. Our first problem came with the fins. Our first original idea was to use these brackets on the roll, but unfortunately it was too unstable when fighting against the wind. The problem was solved using these brackets, obviously top and bottom. This stopped the rotation in the fin and also made it more rigid and resisted the wind a lot more. Our second problem came with the height of the turbine itself. At full height it was very dangerous, as you see, and unstable. When lifting it up it did tend to try and bend and snap. If you look at the end of the, sort of the middle of the pipe, we've tried to design a dowel in the middle which would prevent that bend. Unfortunately, again, top pipe there started to bend, which was another problem. We did try and then prevent that by adding the guide ropes to give it a lot of tension under sort of under the turbine, giving it give it a bit more structure. Again, the problem wasn't solved because the top pipe bent due to the weight of the turbine head. So to make it a lot more safe and stable, we decided to go half height, which give it a lot more structure and a lot more sound, using just one set of guide ropes to give it that tension. And then the last problem we came across was the pipes being crushed and using brackets, so for the base and the turbine head itself. As you can see on the base of the bolts, as it was tightening to the pipe, because it was hollow, we would have crushed it. We decided then to use sort of wooden bungs inside. I'll give it a bit more structure and preventing it from crushing. So there, these.
Charge controller, we bought it offline because it would have taken a long time to build it ourselves and we wouldn't have got something as complex, but it was to stop the battery discharging and powering the motors and to make it so we could have outputs, like USB outputs, to use the power that we're generating. We chose the motor based on the RPM, voltage and current because we needed a motor that was going to have the potential to generate enough power to charge the battery. So we chose 300 RPM because it's kind of achievable on the wind turbine, and then we could gear this further using the motor pulley system. The voltage was two 12-volt motors because we needed to overcome the potential difference of the battery, which is 12 volts. And the current, we were aiming for more, but we actually got about 0.5 amps per motor, but in the future we'd want higher ampage of motors. The spade connectors we used to disconnect and connect the wiring at the joins, such as the pipe joins and the turbine, so that when it's assembled and disassembled, it's easy to kind of take apart the wiring and put it back together. We also used kind of opposite spade connectors on the joins between the positive and negative wires, so they couldn't be mixed up, so that it was going to be wired up in the correct way when assembled and disassembled. Series and parallel was the way that the motors were going to be connected into the charge controller. Basically, series is kind of where the positive end of one motor is connected to the positive end of the charge controller, then a negative terminal of the motor is connected to the positive terminal of the motor, and connected in series. Parallel is where they're both separately kind of connected both together into the charge controller. This did actually have a big impact during the next slide where we talk about testing, about how much kind of voltage we achieved. 12-volt batteries are very common and easy to find, so that's why we chose to use one of them, plus we could get one donated so we didn't have to pay anything for it. The motor pulley system was, as you can see over here, it's all these pulley wheels in the bands that when the turbine's spinning drives the motors, so that you're actually kind of converting that wind energy into actual electricity by turning them. So it's basically wired up with the motors being driven by the pulley system into the charge controller, which are both series and parallel. This then was fed down the kind of stem, down the PVC pipes to the base. Ideally we'd like the wires to sit inside the PVC pipes, but we struggle to do this because we're struggling to feed them in and out. The spade connectors at each stage so that they can be taken apart as they are now, kind of when assembled and disassembled. And then at the bottom, two spade connectors connected into the inline fuse that led to the battery to make sure that there was no kind of electrical issues, so that we had some kind of safety measures.
Was used to measure the electricity in testing when we connected it to these motors, and when the motors were connected in series or parallel, we did 2 tests. The series came out as 12 volts and the parallel came out as 6 volts, and they were both tested at 75 RPM. So the series is when the motors are connected through each other, and the parallel is when it's separate. Stop there. So if you look here, this is where the motor is, and this is the belt here. So the belt was skipping, and so there was a play in the belt, and it causes a jolt in the motors. That's simplified. So we did a test with a 9-volt bulb, and when in series, oh fuck, I was supposed to say that.
Three, two, one.
So we did a test with 9-volt bulb, and when it was in parallel, it
Oh, here's
flicked and
the
was dim.
losing team.
Right,
Go on.
ready? 3, 2, 1.
So we did a test with 9-volt bulb, and when it was in parallel with 6 volts, it flickered and was dim, but it worked fine when we were in series with 12 volts.
Yeah, that'll
Here is a bulb test, and it was connected in parallel, and as you'll see in the video, it came out as dimmer. This is a voltmeter test in parallel.
Wow, would you lot shut the fuck up?
No.
Right, go.
This is a voltmeter test in parallel at 75 RPM, and as you can see up here, this is where the motors would be jolting, and that's the test. Ideal changes, we'd have 1 downpipe instead of 2, and that would mainly be for stability. For the second point, the motor would be changed with an thicker belt, so when the 2 jolts were connected with the belts, it caused like a jolt in the motor, or it'd be skipping. We'd have a different blade bracket, so basically the support bracket wouldn't be needed. We'd have bigger or different shape blades, so it'd be easier to catch wind, and it'd be much better for transport. We'd have a lighter weight material for the brackets, so again it'd be better to catch the wind, and again stability on the downpipe. For the we'd have protection from rust, so we'd anodise the material, so when outdoor it wouldn't rust. And for the final point, we'd have a more advanced charge controller or a smaller battery. So basically the charge controller wasn't as efficient, and when it showed, it wouldn't really show much of the voltage that was being produced.
Embarrassing bodies, and here's Cameron talking about his body. Hi, I'm Max. I'm here with proxy with Cameron for his chronic diarrhea, and I'm going to be talking about the future uses for the project thing. Can we use in third world countries and for camping? Well, with the camperman.
Slide is on the maintenance. So the first point is you could have different weatherproof materials, for example titanium or aluminium, and they'd be used for the pegs and the brackets, etc. And then you could anodise or use protective coating, which is like a paint, over certain materials, so like on a previous slide where that could be an ideal change.
We'd also oil any of the moving parts, such as the chain and the wheel, and when the belts started to perish or stretch, we'd replace them.
An active role of kind of keeping track of the finances and costings, because we had a budget of £90 made up from £15 per person on our team. So we kept a running total along the project, so we knew that we weren't going to overspend, but cost was never a concern because we were getting a lot of parts cheap from various departments in the college, and some were donations. This table is all the kind of structure parts. You can see the costings down the side, the materials, where they were sourced from. Everything here sourced from departments in college, so it was bought kind of cheaply in bulk. And all of those overestimations of how much it would actually cost to make sure that we were getting the costings right, and that we were taking into account any wastage or mistakes. This is similar. This is kind of all like the turbine parts. The bike wheel and the wheel quick release were all donations. They're from the engineering department and other ones, so they're just overestimates again. This is all the electronics. The battery, 12 volt leisure battery, was also a donation, so that came at no cost. And then a lot of these parts we had to order from Amazon, and they're slightly kind of rounded up to make sure that we kind of, you know what I mean, we weren't under costing. The total of all of that came out as £87.75, which means that we were on the budget, and that's particularly impressive seeing as we overestimated a lot of the costs.